Hi students, in this session we'll solve a numerical problem to find the fault MVA or the short circuit MVA when a three-phase ground fault occurs in the system. We will also find out the current limiting reactance value that should be inserted in this system in order to reduce the fault MVA by 50%. We have two generators in parallel. Both are having a voltage of 11 kV, and the first generator has an MVA rating of 10 MVA. Its reactance is 25%. The second generator also has the kV rating of 11 kilovolt. Its MVA rating is 20 MVA. Its reactance is 40%. This 25% reactance is same as 0.25 per unit. Let me write this as 0.25 per unit. This 40% reactance is same as 0.4 per unit. Now let us choose the rating of second generator as the base values, because the second generator is having bigger MVA rating. So MVA base new equals 20 MVA, and the KVB new equals the base kilovolt. This is equal to 11 kV. In order to solve the three-phase ground fault problems or the symmetrical problems, symmetrical fault analysis, this is the approach we are using. After choosing the base values, we need to draw the reactance diagram and mark the per unit reactances. Then we have to find out the Thevenin's equivalent circuit. At the fault point. Then we can find out the fault current or the fault MVA or the short circuit MVA. This is the approach we are using to solve the three-phase ground fault problems. So now we have selected the MVA basis. Let's draw the reactance diagram now. We have two generators in parallel. This is the first one. This is the reactance of the first generator. The second generator and its reactance. These two generators are operating in parallel. Now this is our feeder. The feeder reactance is not given in the problem, so we can neglect the feeder reactance. The voltage of the first generator and the second generator both are having 11 kV. Our base kilovolt is also 11 kV. So the per unit voltage will be the actual voltage of the generator divided by the base kilovolt, which is equal to 1 angle 0 per unit, or it is 1 plus J0. So the voltages can be marked as 1 angle 0 per unit. For both generators, the voltage is 1 angle 0. Now let us find out the reactance values of these two generators. Now if you look at the problem, for the first generator, the reactance is 0.25 per unit. This is given on a base MVA of 10 MVA. And the second generator has a reactance of 0.4 per unit. This is with a base of 20 MVA. So these reactance values are given with a different bases. But we have to find out the per unit reactances on a common MVA base. So let us convert all the reactances into a common MVA base. Let us find out the reactance of generator G1. This is the formula we are using. X per unit new equals X per unit old into kVb old divided by kVb new the whole square into MVAB new divided by MVAB old. So this is equal to X per unit old of the first generator is 0.25. J 0.25 per unit into kVb old is the rating of the generator G1. It is 11 kilovolt. kVb new is 11 kV. The whole square into MVAB new is 20 MVA. MVAB old is the rating of the generator G1. Now this X per unit old is given with old base values or with the rating of that equipment. We have to find out X per unit new with new bases. And this is equal to J 0.5 per unit. Now let us find out the reactance of G2. Let me mark this reactance here. It is J 0.5 per unit. When you find out X per unit new for the generator 2, this will be same as the X per unit old. Because the rating of the generator 2 is taken as the new base values. As the new base values and the rating of the machine both are same, this X per unit old and X per unit new will be having the same values. Or even if we substitute the values, we will get the same value here. And this is equal to J 0.4 per unit. Now let us find out the Thevenin's equivalent circuit. In the Thevenin's equivalent circuit, we have a voltage source and Thevenin's impedance. This is our Thevenin's voltage VTH. It is the voltage available at the fault point before the occurrence of fault. And this is equal to 1 angle 0. This voltage will be available across these two terminals because before the fault, before the occurrence of fault, the circuit is opened. So there is no voltage drop here in the reactances. So this 1 angle 0 per unit voltage will be available here. So VTH is equal to 1 angle 0. What is ZTH? This is the impedance at the fault point before the occurrence of fault. This is equal to the parallel combination of these two reactances. J 0.5 parallel with J 0.4. This is equal to 0.5 into J 0.4 divided by J 0.5 plus J 0.4. And this is equal to J 0.222 per unit. This is the Thevenin's impedance, J 0.222 per unit. Now let us find out the fault MVA or fault KVA. The fault MVA is equal to the MVA base divided by the per unit impedance. The per unit impedance is same as the Thevenin's impedance at the fault point before the occurrence of fault. So MVA base nu is equal to 20 divided by our Z per unit is J 0.222 per unit. And this is equal to J, this is 90 MVA, or this is equal to 90,000 kVA, because in the question we are asked to find out the fault kVA or the short circuit kVA. It is 90,000 kVA. In the second part of the question, we have to find out the current limiting reactance that is to be included in the feeder circuit, so that the short circuit MVA or the fault MVA is reduced by 50%. So how much feeder reactance should be included here, or how much current limiting reactance should be included here? So the fault MVA reduced by 50%. So you know the fault MVA equals 50% fault MVA means 90 divided by 2, this is 45 MVA. So in order to limit the fault MVA at 45, what should be the reactance? What should be the current limiting reactance included in the feeder circuit? This is equal to MVA base nu divided by the Z per unit. Our new fault MVA is equal to 45. This is equal to 20 divided by the Z per unit. Our Z per unit is equal to J 0.444 per unit. So we need to have this much of reactance in the entire power system in order to limit the fault MVA at 45. So how much reactance we are having in the system at present? It is J 0.222. So what should be the external reactance that is to be included? So X external is equal to the total reactance required, J 0.444 minus the reactance we have at present, J 0.222. This is equal to J 0.222 per unit. Now let us find out the actual reactance, which is equal to per unit reactance into the base impedance. Let us find out the base impedance. ZB is equal to KVB nu the whole square divided by MVAB. Or KVB is equal to 11 divided by MVA base is 20. So our Z base is equal to 6.05 ohm. So the actual external reactance to be added is equal to the per unit reactance into, this is our per unit reactance, into the Z base. This is J 0.222 into the base impedance is 6.05, and this is equal to 1.34 ohm. So this much of reactance should be inserted in the feeder circuit so that the fault MVA can be limited at 45 MVA.